So today we're going to cover a couple topics. So the first thing we're going to do is finish talking about the differences estimator. I'll talk a little bit also about how you do statistical tests. Nothing really like technical, more just making sure you can understand the underlying theory behind it and then how you actually would do it in practice. And then after that, so that's going to be the end of the current lecture slides. And then we'll start talking about what we call the VSL, which is the value of statistical life. So when people talk about economists putting a dollar value on life, basically this VSL literature is what they're referring to. So those are that's the next set of lecture slides, lecture 7. Okay, so the last time that we met on Monday, we were talking about the differences estimator, which basically will, the way it works is you have like a treated area. So in our scenario, it was Los Angeles, and you have a control area that wasn't affected by policy, whose effect you're trying to estimate. So in our example, that was San Diego. And then you take the difference, basically the change in the outcome in Los Angeles, and the treated area compared to the change in the outcome in the control area, which was San Diego. So it turns out it's also possible to implement this estimator using a linear regression. So in order to do that, we have to define several indicator variables, several dummy variables. So the first one that we're going to define we'll call time. So we're indexing it by both I and t, although since it's really just a time indicator, it's only going to vary with t, the time dimension. It's not going to vary across counties. And so that's going to be set to be equal to, it's going to be a variable equals 0 if you're looking at an observation that's prior to the policy being enacted, and 1 if you're looking at an observation that is post, like after the policy being enacted. Then the next dummy variable that we're going to define will be called Los Angeles, which I think should be pretty straightforward. It's going to be equal to 1 if the observation you're looking at corresponds to Los Angeles County, and 0 otherwise. So in our scenario, it would be like 0 when you're looking at San Diego County. And then finally, we're going to define a variable which we call policy, which is going to be equal to 1 when the policy is in effect in the county and time period that you're looking at, and 0 otherwise. So the only time that the policy variable is ever going to be equal to 1 is when you're looking at the treated area, which is Los Angeles, during the post-policy period, which is, I think in our example, is like after 2010. So if you wanted to, you could also have, or you could sort of construct policy by actually just doing the interaction between that time indicator and the Los Angeles indicator, right? Because this interaction, once you multiply both these together, this interaction is only going to be equal to 1 when you're in Los Angeles in the post period, and otherwise it's always going to be equal to 0 because at least one of these two variables will be equal to 0, and in some cases both. Okay, so now that we have those, now that we've defined those variables, we can consider the regression that I'm going to claim is going to give us the differences estimate. So it's going to be a regression of the outcome of interest, which in our case is hospitalizations, on first of all that time indicator, second of all the Los Angeles indicator, and then finally this policy variable. So the coefficient that we're going to be interested in here, the coefficient that's going to give us the effect of the policy, is in fact beta 3, the coefficient on policy, as you might imagine. But we'll get there. So if we kind of ignore that residual term, so the residual term is basically, we think of it as being like statistical noise, all the other determinants of the outcome that aren't in our model. So we're going to set that aside for the moment and just think about what basically like what the different coefficients mean. So if we look at beta naught, which is an intercept, which is the intercept in this regression, if you think about it for a moment, you'll see that beta naught should estimate the value of y during the pre-policy period in San Diego. Why is that? Because if we're in the pre-policy period in San Diego, then we know that the first variable time is set to 0 because we're in the pre-policy period. We know the second variable, Los Angeles, is set to 0 because we're in San Diego, not Los Angeles. And then we know for sure that that third variable, policy, is set to 0 because we're both, our policy is basically the interaction between time and Los Angeles. Both of those are 0. So definitely policy is 0. So all three of those variables are 0, and that leaves only beta naught. So beta naught is actually going to estimate the average value of y in the pre-policy period in San Diego. Then if we want to think about what's going to estimate the value of y in the pre-policy period in Los Angeles, you could go through and you realize it's going to be beta naught plus beta 2, right? Because basically what we're saying is now we're in Los Angeles, so that Los Angeles dummy turns on, but we're still in the pre-period. So time is still set to 0, and policy is still set to 0 because it's the interaction between time and Los Angeles. So now the only two coefficients that are going to appear are beta naught plus beta 2. So that's going to give us the average value of y in Los Angeles prior to the policy turning on. Then if we want to think about the post-policy period in San Diego, it's going to be beta naught plus beta 1 because time has now turned on since we're in the post period, but we're still thinking about San Diego, so Los Angeles is off and policy is off. And then finally, if we want to think about the post-policy period in Los Angeles, which is the treated area, that's the point at which it's equal to all four of those coefficients summed up, right? Beta naught plus beta 1 plus beta 2 plus beta 3. Because at that point, all three of those variables are going to be turned on. You're in the post-policy period and you're in Los Angeles, and then the policy is in effect, of course, because you're in the post-policy period in the treated area. So now if you think about, okay, well, what's the difference in the diffs and diffs estimator? We said it's the change in the outcome in Los Angeles, which is y11 minus y10, subtracting off the change in the outcome in San Diego, which is y01 minus y00. And so we can plug in for all of these coefficients that we just defined. We can basically plug in different sets of coefficients for each of these values for y11 and y10 and so forth. So y11 is the post-policy period in Los Angeles. So we said that was all four coefficients summed up. So I got that right there. Y10 is the pre-policy period in Los Angeles. So we said that was beta naught plus beta 2. So I put that in there, subtracted, of course. Then the post-policy period in San Diego, that's y01. We said that was beta naught plus beta 1. So I put that in there. And then finally, subtracting out y00, which is the pre-policy period in San Diego, we said was beta naught. So if you do, basically a lot of these terms are going to cancel out with each other. And if you kind of go through, you're going to see, okay, it's going to be beta 1 plus beta 3 after I cancel out everything in the first set of parentheses, then minus beta 1, then those two beta 1s cancel out. And so you end up with just beta 3. So we wrote down the diffs and diffs estimator, and then we plugged in the equivalent regression coefficients for each of those quantities. And what we found is that the diffs and diffs estimator, in fact, is going to be equal to beta 3. But that's the regression coefficient on the policy variable. So if we run that regression that I posted at the very top of the slide there, and then take the coefficient on beta 3, what we've shown is it's going to give us the diffs and diffs estimator. So the estimate, it turns out that the way that I set this up is actually going to be like not just sort of equal on average, but it'll be exactly equal to the diffs and diffs estimator. So this is a case where you're like literally generating the same estimate that you get from doing diffs and diffs using the regression. In general, like in a lot of the papers that we look at, they won't literally be sort of estimating like exactly a differences and differences estimator as we described it, but they're going to do something that is sort of for all intents and purposes equivalent. And the way that they do that is that they're going to include variables that both control for time trends and control for what we call like cross-sectional differences between different areas. So in the regression that I wrote up there for the Los Angeles case, that time coefficient, the coefficient on time IT, that's basically controlling for a time trend because what it's going to do is control for any change in y that's jointly shared between both Los Angeles and San Diego that is occurring over time. So you can see that so this is like a case where we're literally actually like estimating differences and differences design, but you can basically see that if you're sort of thinking of regressions that control for aggregate time trends and control for cross-sectional differences between areas, then this regression is controlling for aggregate time trends because it's got that time indicator. then it has that Los Angeles variable in there. So the coefficient on Los Angeles is going to describe how the outcome differs in Los Angeles versus San Diego in the pre-period, basically like in ways that are fixed over time. So to the extent that the two counties are on like different trajectories and trending differently, it's not going to pick up those differences because this isn't a variable that changes over time. It's always just equal to 1 if you're in Los Angeles in any time period, and 0 if you're in San Diego in any time period. So it's going to control for factors that are different between those two counties but aren't changing over time. And so in that way, then it's basically including what we're calling these cross-sectional dummy variables. So you want to think of the different states or counties or cities in your data set as being these cross-sectional units. So given that we have those two sets of controls, the aggregate time trends and the cross-sectional differences, the cross-sectional dummies, the only factors we need to worry about are actually factors that change over time differently for Los Angeles versus San Diego. So that's, I mean, similar to exactly what I was saying earlier when we were talking about differences to begin with, that what you need to think about is whether or not San Diego basically gives you like the counterfactual trajectory for what would have happened in Los Angeles had there not been the policy implemented that in fact was implemented. So to the extent that the changes in the outcome in San Diego are a good representation of what would have happened in Los Angeles, then you're going to get an unbiased estimate of the policy effect. If they're not, then you won't. So most of the, not all, but most of the studies that we see are going to have this either literally be like a differences and differences study, which we'll see some examples, or basically have a flavor of a differences and differences study in the sense that they're going to have like panel data sets, so they're going to have data on different areas observed multiple times over time, so you have both this like cross-sectional dimension and this time dimension, and then they're going to control for aggregate time trends that are affecting all of the cross-sectional units similarly, and they'll control for cross-sectional differences between those different units that are fixed over time. Okay, so then the last thing that I want to talk about here in terms of the empirics is that up till now, we've been thinking about coming up with estimates, but not really talking about how we quantify how much like variability might be in those estimates, and in particular, whether or not an estimate that we get represents a true effect or might just be due to chance. So like the most basic demonstration of that would be, let's suppose that we're doing the comparison between Los Angeles and San Diego, and we see that Los Angeles hospitalizations increased by like, or I guess ideally we'd like to see a decrease because we're talking about pollution control policy. So let's say that Los Angeles hospitalizations decreased by like 6% during the pre to post period, whereas in San Diego they increased by 1%, right? So if you wanted to do the difference and differences estimator, then you have to take the difference between those two changes. So you have a minus 6% for Los Angeles, and then you subtract off the 1% for San Diego, and you end up with like a 7% different estimator. But it wouldn't be clear. So if I just told you that was the estimated effect, it wouldn't necessarily be clear to you whether or not the policy actually had an effect, right? So let's ignore the fact that there might be some sort of omitted variables bias, like there might have been some other policies or some other sort of factors changing in Los Angeles that would drive down hospitalizations and expectation even absent the policy. Even if you're not worried about that, you still don't really have a sense of what the year-to-year variability in hospitalization rates is for each of those counties, right? So you're like, well, I see that Los Angeles had a decline of 6%, but maybe like in the average year they might just have an increase or decline of somewhere between 5 to 10% regardless. And so it was essentially just random that we happened to see the 6% reduction during this time period. But if we ran the sort of experiment many times again, obviously you can't because you only have that one observation on Los Angeles in that given year. But if you were able to sort of run that experiment many times, maybe on average there would have actually just been a 0% decrease. So the question here that we need to answer when we're talking about statistical significance is whether or not basically whether or not the change that we actually observed was large enough to be due to chance, or was sort of a magnitude that would be reasonably possibly due to chance, or whether it's too large to be due to chance if we assume that there was no actual effect, in which case we would reject the hypothesis that there was no effect and conclude that there is an effect. So essentially when we talk about statistical significance, what we're talking about is the probability of observing a coefficient that was large, or a change that was larger than the one we did, if the true coefficient is equal to 0. So let's just assume we have a very simple regression model up here, and we have some data, and so we fit the line that relates x and y, or that best summarizes the relationship between x and y. So in any finite sample, unless you have an infinite number of observations, it's not going to be the case that beta 1 is exactly equal to 0. So even if there's no relationship between x and y, so that in expectation beta 1 should on average like be equal to 0, it's still not the case that if you actually go in and fit the relationship in a sample that has some less than infinite number of observations, it's still not the case that you're going to get an estimate that's exactly equal to 0. And that's that's true even when there's no true relationship between x and y. So the true coefficient here, the one you want to think about, or the one we like to estimate, is basically the one that we would estimate if we had an infinite amount of data, which technically we never have. So what we want to do is determine whether the estimate of beta 1 that we get represents a true relationship, or whether or not it's just statistical noise. And it turns out that using statistical theory, we can derive the distribution of that coefficient, of that estimate of beta 1, under the assumption that the true coefficient is 0. And if we do that, then we can express how unlikely it was to find a coefficient, find an estimate of beta 1 that was as large as the one that we observed. So let me try to make that a little bit more graphical as well. So most of you are probably familiar with say the normal distribution. So it turns out that most of the coefficients, like most of the regression coefficients that we get estimates of, are distributed approximately normally, not exactly normally, but sort of close enough to treat them as being distributed pretty much normally. And so the idea here is that so this is going to be what we'll call beta hat 1, and this is going to be the origin. And so beta hat 1, so this is the beta hat 1 is the regression coefficient, right? So we've got a bunch of data. yi, this is xi, and we fit a line through these data, like the best fitting line. And the slope of this line is going to be equal to beta hat 1. And so the variation, basically the variation in that slope is less than the variation that you would observe in, say, y. So y is distributed even at a given value of x. There's like a substantial variation in what y could be. We have some observations that goes all the way up here, some observations that are maybe half that value. So there's variation in y. And if you were to sort of rerun the experiment, so if you basically, maybe the easiest way to think about it is like, x is a education and y is earnings. So you're sort of interested in estimating the relationship between education and earnings. And so in order to estimate that relationship, you're going to draw data out of the census or current population survey, let's just say the census, where you can observe information. You can draw individuals, you can observe what their education level is and what their wage level is. So each of these observations is basically a single individual with their wages on the or their education on the x-axis and their wages on the y-axis. So if you just draw a sample of 100 people, you're going to estimate some relationship between education and earnings. It turns out that the relationship you're going to estimate is probably on the order of like 7 to 10% in the sense that a 1 year increase in education is associated with about 7 to 10% higher earnings. But you draw some sample, say 100 people, and you might estimate a slope of like beta hat 1 is equal to 6%, right? So it's like pretty close to the 7% to 10% range. Then you draw another sample of 100 people from the census. Remember, the census has over 100 million people in it. I mean, about 100 million households. Technically, about 300 million people in it if you were able to get data on all of those people. And so you're going to get another estimate of beta hat 1, but it's not going to be equal to 6% probably. Then for your second sample, maybe you get like 8%. And then for your third sample, so you put that sample back in, draw another sample, which an expectator like almost really will have no overlap with your first two samples, just because you're drawing such a small fraction of the total census. And maybe you get like 9%. You can do it again, and maybe you get like 5% or something. So basically, on average, the way that I'm like describing these beta hat 1s, you can see they're kind of distributed maybe around like 7 or 8% on average. But in any given finite sample, there's always some variation, right? So you could think about doing this. I mean, you have a sample of like 100 people, but in theory, you could draw like hundreds or even thousands of samples from the U.S. Census and run this regression like 100 or even thousands and thousands of times and save the slope coefficient that you get from that regression for each of those iterations. And what you would do, or what you would find then, is that when you took all of those slope coefficients and then plotted the distribution of them, so basically made like a histogram of what the distribution of those slope coefficients, you would find something that looks like this after you smooth it. So actually, this would be like let's just say that the true relationship that you could observe if you drew a sample of the entire census, so you had like 100 million observations. Let's say the true relationship that you would estimate was like 7%. So what you would find is that your distribution of regression coefficients of these beta hat 1s would be centered around 7%, but there would be a substantial amount of noise. So maybe some of them would be as high as like 11% on the high side, and some of them might be as low as like say 3% on the low side. So you would actually find something that looked pretty close to a normal distribution for these coefficients. So it turns out that that's a description of sort of like a sampling process that would allow you to actually map out the distribution of beta hat 1. In general, you can't just draw like an infinite number or arbitrarily large number of samples from the larger population like that, because usually you just have some data set and use the entire data set. Like you would never just use a subset of that data set, because you can always get more precision by using more observations. So you can't do this in practice, but it turns out that using statistical theory, we can basically derive under some like pretty loose assumptions. We can derive what the sampling distribution of the regression coefficient should be. Okay, and in particular, what we're more interested in, so if we want to see, let's say that our question is whether or not there's any return to education, like whether or not people who have more education do in fact earn more money, right? The null hypothesis in that case would be that there's no relationship between education and earnings, and so we would think then that under that null hypothesis, or we could show that under that null hypothesis, the regression coefficient would have a distribution that was centered at 0% and have basically some dispersion around 0% that we could quantify. So let's say we basically are able to represent the sampling distribution of the regression coefficient, and then let's say that we actually observe. So let me say the actual estimate. So let's say that we have, we've drawn the sample then, and we estimate a 6% return to education in our earnings, or in our little sample from the census. So given that we know that the distribution under the null hypothesis of no relationship between education and earnings looks like this normal distribution that's centered at 0%, and let's say it had a standard deviation of like 1%, so basically what that would mean is that it's getting very close to having almost no probability mass once you get up to plus or minus 2%. So if we were to observe an actual beta hat 1 then of 6%, what we would conclude is that one of two things has occurred, right? Well, actually, there's sort of one of three things that could occur. So the first possibility is that we got this entire distribution wrong under the null hypothesis, and our standard errors are screwed up. But let's assume we got it right, because usually we do. So the second thing that we could have that we may be observing is that we basically have had an outcome here, like a realization of beta hat 1 that is incredibly unlikely. So the way that I drew this sampling distribution under the null hypothesis and under the assumption that we actually observe like a regression coefficient of 6% instead of 0% in our data, there's essentially less than a 1 in. This is like a t-stat 6. So we're talking about less than like a 1 in 100,000 chance that we would have observed a coefficient this large or larger in magnitude under the null hypothesis. There's no relationship between education and earnings. So either we've observed something that's incredibly unlikely to happen, or this null, or basically the distribution under the null hypothesis is not the actual distribution of beta hat 1, which is to say that the null hypothesis is false, right? So if the null hypothesis is false, that means that the true beta 1 is not equal to 0%, but rather it's going to be something that's greater than 0%. That's the point at which we would say we rejected the hypothesis that there is no relationship between education and earnings and concluded there is a statistically significant relationship between education and earnings. So that's basically how hypothesis testing works. You sort of say like, look, here's what I know reasonable values of the regression coefficient could be under the null hypothesis.